Okay, so what does the word significant mean? I think this is one where people use it all the time, and then very often it turns out they had something else in mind. Let's see what it means. All right, pretty split. 2-2-4. So none of the votes got more than 50%. So I think that means you guys have to talk to each other, and we'll revote. So talk to your neighbors. We're gonna revote on this and see what you guys think.
So you can have a really small effect. So when you're 6, right? But that can still be significant.
For me, the main thing is like if the effect is insignificant, it's most likely due to chance. So the converse is my answer.
If you have a very small, additionally, if you have a very small effect, but also very small standard error, then it can still make the effect significant, even if it's very small. It just also depends then on the standard error.
Okay, let me reopen the voting. So it's the same exact question as before, but now you're allowed to change your mind. So same 3 possible answers. What does significant mean? You might have to scroll to the bottom, I'm not sure.
That's the benefit of the conversation. We don't change our minds. Just talk and then we just stick to what we think.
Yeah, maybe everyone wants to say the same. I don't know. We'll see.
There's one word, if it was there, I would be like 100%.
What word is that?
If it's relatively large,
Oh.
I would definitely go for it.
Okay, but then see the thing is, if someone says relatively large, what they're hiding is relative to what, right? So yes, I mean yeah. So then the question would be, what does relatively mean? Yeah.
To the comparison to similar problems, perhaps. I don't know.
It is true. Okay, all of these could be like relatively like there is low uncertainty in the effect. It could be like, you know, the size of the effect is large compared to the uncertainty. So relatively large could be all 3 of these. The effect is unlikely to be due to chance. Okay, how is that relatively large? The probability of the effect is large, right? Like so. Yeah, you gotta really like understand what these things mean, and I think it's actually not easy. I think it's really easy. This is why we do this stuff in class. It's like really easy to watch the video and be like, next video, like, and then like you gotta pause and be like, wait a second, nothing actually makes sense. Okay, so we're up to 8 responses. Let's see, did anybody change their minds? Let's view. Okay, now we're at 3-3-2. Okay, so one thing. All right, I think the effect is large. Let's start with this one. This one is the most vague out of all of them, right? Like the other ones have, first of all, they have more words. What does large mean? So maybe somebody who voted for this one can tell me what they interpreted large to mean and why significant is the same as large. Yeah.
I considered significant as large.
Okay.
Partly because we use it in conversations.
Yes. Okay, so this is absolutely true, is that in real life, when you say significant is a synonym for large, right? If somebody crashes a car into your house, there was some significant damage to my house. We're talking about a lot of damage. Like, all right, so this is the first thing. In stats, significant and large are different. It is not the same word. Of course, it's related somehow to the size of the effect, right?
But I had another observation during the video.
Okay.
The presenter, he spoke about 0.6 something, and he said that was significant.
Okay.
Because the values similar to this are usually 0.01, and we get excited when we find that. So
Right. Okay. So this is true. So it has something. Obviously, it has something to do with large, right? Like in real life, we use large, and it means the same thing as significant day to day. So in stats, it's got something to do with the size. But I think you should delete from your brain that it's a synonym from large, right? It's got like some specific other meaning that has something. Of course, it has something to do with large. There's a lot of math words like this, right? Like let me think of one from linear algebra or something. Yeah, I don't know. Like when in linear algebra, when you say like independent or dependent, right? It has a very specific meaning. It's not like I'm an independent, I don't need no man. Like it's not like that, right? Like it has a very specific meaning about the coefficients, and same with this, right? So there's a very specific meaning, and like if I just ask you what is the actual specific meaning, of course it's none of these three, because none of these are specific enough. So this is really like a translation through a couple layers. One, you have to actually know the real definition, and then you have to translate it, and which of these is the closest. And I would say none of them are perfect, but one of them is better than the other two. Okay, so it has something to do with large, but I think the effect is large is the most misleading one that people get wrong most often. And I have a little diagram here. So I think to make it really simple, let's think about estimating one number. So we're going to estimate the mean of some population, and we just want to know is the effect is just whether or not the thing is zero, right? So like imagine we have a bunch of patients and we treat them with something. Sometimes it helps them, sometimes it hurts them, and we just like measure and we want to know, is it helping? Is the effect of the like treatment we're giving these people significant? And of course the problem is in real life you're kind of used to numbers being numbers, but as soon as there's randomness involved, nothing is a number, right? Everything is a probability distribution, and sometimes it helps, sometimes it hurts. We want to know when. So I want you to compare these, the orange curve and the red curve. Let's look at these. So the orange curve and the red curve. And they both have a similar mean, and the mean is quite a bit far from zero. So you kind of like, on average, it seems like the people, if it was the red curve, that was like what happened, that on average is pretty close to this number. That's pretty good. Let's give this number a name, just to be, so we can talk about it. Let's call this number 3. So the mean is 3. It looks like it's most of the time it's 3. This is supposed to be the probability density function, not the thing you view files in, but the probability density function. So a lot of the time it's really close to 3. Very rarely you get like 2.5 or something, but this is like a big effect, right? 3, we're pretty sure it's 3, big number, we're quite confident it is. So this is definitely significant. Now the orange one, I tried to draw it, so the orange one had the exact same mean. So the orange one, the mean of the orange one was supposed to also be 3. But the orange one is different in that it has a very wide PDF, right? So even though the size of the effect is the same as the red one, like on average they're 3, if you take the average of the red group and the average of the orange group, they're both 3. I would say they're both large. There's something about this orange one that's not satisfactory, and that's that we're not very sure, right? It could be that it's actually not helping. It could actually be negative. And so that's why I think large is misleading. Large is sort of deleting one of the dimensions, right? Large is just about size. It's like, take this problem and pretend it's a one-dimensional problem. Is it small or big? And it's not a one-dimensional problem. It's got something to do with 2 dimensions. And so that's why I think the effect is large is misleading. Of course, like I said, none of these 3 sentences are perfect. So in some context, you're just like chatting to your data science friend. You're like, oh yeah, it's a large effect. Like it makes sense. If you both know what you're talking about, you can say that and move on. But in this context, I'm going to say the effect is large is wrong. Okay, so one of the other 2 I think is the most right one. And it was pretty split, 3-2. So take another chance. Now you guys know that the effect is large is the wrong one. Maybe someone from this 2 group, you guys should convince the effect is large people to join you. And then you'll have a majority and you'll win the vote. So we're gonna do the vote one more time. So yeah, chat. Yeah, okay, maybe you have to turn around and chat with the people behind you. I don't know.
We're saying is unlikely to be due to chance. The effect is unlikely to be
He said that as well, right?
Yeah.
One with the Z.
What do you guys think?
Be the same.
Yeah. And what would it take to convince you that it's the other?
Okay, so it is open again, so you can vote for a 3rd time. Okay, I'm up to 5, 6. I'll wait till we get to 8. Okay, 8. Okay, let's see what you guys said. So same questions before. Hopefully nobody pressed the effect is large. Oh wow, very split. Okay, let's talk. So I have some more examples here. Maybe these will help. But maybe let's hear from one person who voted for each on why that one means significant or why they voted for that. Yeah.
So I voted for the top one there. I'm going to give you a chance.
Okay.
And I think the best way I can explain why is you calculate a p-value when you're doing.
Okay. So what is the p-value?
The p-value is the probability that you achieve an answer equal to or I think greater than the answer that you got if there actually was no relationship.
Yeah.
So if you have a very small p-value, you have a very small probability.
So the p-value is somehow the thing in the sentence. It's like the chance, or the chance that the effect was due to just like pure randomness is somehow the p-value. And if that's low, then you're like, that's significant. So this is your connection. You're like significant p-value, chance, that's the connection. Seems plausible. Okay, but now we have 7 people and there is low uncertainty. So maybe somebody from the low uncertainty group can say why they voted for that one. Most people here voted for low uncertainty. You got scared off by him. He's not that good. He doesn't know anything. Yeah. Go ahead.
It seems to me the second option has to do with finding the estimate between minus two variance
Right.
and plus two variance.
That's the confidence interval.
Yeah.
Yeah.
But the first one, I selected the first one.
Okay.
And I thought it is the reason why in the video described 2 methods
Right.
to find it. One with 2 variants before and after, another one with p-value. I guess almost they are. He himself insisted that they are almost the same.
Right. Yeah.
But it seems to me if you decrease the level of uncertainty, it's going to be closer.
Yes.
To the fact rather than, let's say, saying.
This is definitely a good point, is that the lower the uncertainty is, the more it should be significant somehow, right? But that was the same thing for the size of the effect, right? The large, that I told you was the wrong answer. So let's look at the board, and I think let's look at these examples. So this red one, right? Red one had low uncertainty and was a large effect. And so it's definitely significant. And then the orange one had a large effect, like the mean was 3, but it had a lot of uncertainty, so we were like, oh, maybe it's not significant. So it's got something to do with both. And let's look at this green example. So this green example has low uncertainty, but it's right around 0. So even though the uncertainty is very low, like we're very sure the green is somewhere between here and here, it's not a very significant effect, or maybe I should avoid the word significant if that's what we're trying to talk about. Even though the green one has very low uncertainty and we're very sure it's between this and this, maybe it has no effect at all. Because like actually, even though we can narrow it down between these 2 small numbers, 0 happens to be in there. And so like maybe it has no effect. So with like a high probability, there's a chance it does nothing. So just like the 2 dimensions of this thing, right? In all of probability, there's the mean, that's like the size, and there's the standard deviation, or if you want the variance. Let's write square root of the variance so we can be super precise. And this is like the uncertainty size. Okay, and the problem with something like significance is like your human brain really wants to one-dimensionalize things and turn it into what is the one thing that matters. And the problem is there's 2 things that matter, right? So if you forget one of them, you're going to make a mistake. So the mean is like how far you are, the size, but the variance also matters. And actually how they combine matters. It's not just enough to look at one or the other. So that's why I would say, going back to this, there is low uncertainty in the effect. I would say that doesn't necessarily mean it's significant, because the uncertainty in the effect to me is like the square root of the variance, like how much of a spread there is in what you know. And if that includes 0, then maybe it's still not doing anything. It's not significant. So I think the most correct answer is the effect is unlikely to be due to chance. Is the reveal going to work? No, the reveal isn't going to work. Okay, I don't know what's going on. So that's the one I would pick, unlikely to be due to chance. And this is exactly what this hypothesis testing thing is, right? So the hypothesis testing says, pretend everything was due to chance. Let's calculate the p-value. That's the probability of seeing what we're seeing completely due to chance. And if that is low, if the probability is low, then we say it's significant. And again, I think the best way to think about it, and this is what they said in the video as well, is to only ever think in terms of confidence intervals. And confidence intervals somehow combine both of these things, right? You have a lower bound and an upper bound. They're combining the mean with the square root of the variance. They're saying here's the minimum thing that we could think could happen. Here's the maximum thing that we think could happen. And so, we haven't turned it into a one number. We've turned it into two numbers, and that somehow is enough to capture what's going on. So for these ones on the board, the way you would draw the confidence intervals for the red curve, you have like the lower and the upper bound are both very near 3. And so it's definitely significant because we're quite confident that it's far out from 0. Like we're 95% sure it's somewhere between 2.9 and 3.1. Whereas for the orange curve, it's so big, the uncertainty is so large that it actually includes 0. And that means that maybe 0 could have happened and we just got unlucky, right? So the confidence interval somehow captures that. For the green curve, again, you have a very small confidence interval. That means you're quite sure of where the effect is. But if it includes 0, that's no good. That means it could have happened by chance. And the yellow one is like bad in both ways, right? It's near 0 and it's a big uncertainty, so you certainly don't know anything. But yeah, I think this is something really important to remember, is kind of like your entire life has been about one number, like how big is the thing? What is my grade? What is this, right? And you gotta switch to thinking in terms of probability distributions, or at the very minimum, 2 numbers, right? You can't think about one number. Okay, any questions or comments about that? This is, depending on how your stats class was when you were in undergrad, this might be reviewy or it might be completely new. Okay, so something to keep in mind. And again, yeah, like I think it's very easy to get confused with the hypothesis testing and then like the null hypothesis and like it's like what the hell are you talking about, man? Like just if you're like that and you're like me, just think about the confidence interval. I think that's the way to do it. No numbers ever in data are actual numbers. It's always some uncertainty, right? And that's how you should think. So when someone tells you the number is 3, you go, no. The number's not 3. It's on average it's 3. What are we talking about here, right? 2.9 to 3.1, that's significant because it doesn't include 0. That's the easiest way to see it. Okay. All right, so if there's no more questions on that one, let's go on to the next one. So today is basically going to be a bunch of stuff like this. And I think I ruined the next question, which is what's the better way to understand if the effect is significant? Look at the R² value or look at the confidence interval. But let's skip this one because I just told you. So a lot of people get confused between this. So the R² is somehow telling you, again, it's a different measure of the size of the effect, right? So the R² value is telling you how much better it is in a regression, how much better it is to use the regression than to just use the mean. So the R² is how much better. Oh, I guess I shouldn't erase that. Let me get that number. So you really should think of the R². This is how I think about it. It's how much better. How much better the regression is than nothing. And by nothing, I mean than using only the mean. Okay. So a lot of people kind of overuse R²s. And they get excited when they see a high R² value, which can be exciting. But I think it really is just like you really should think of this the same way you think about the RSS, the residual sum of squares. The residual sum of squares is that what we calculated. It's the expected value of the true thing minus what you think it is, minus your estimator. Let's say y minus y hat squared. So it's they're both kind of just measures of how far away you are in the root mean squared error sense, in the mean squared error sense. The R² is just a ratio of involving this. It's kind of like normalized to be between 0 and 1. This one is just as useful. So like if somebody deleted R² from existence and we only had to work with this one, we wouldn't really lose a lot of sanity. It would be fine. So that, and I think this one's very clear. This is like how far you are off on average, well squared. But that one makes sense to me. And this is what we did. We did this last week and the first week quite a bit. Okay, so I guess I spoiled that one a little bit. But any questions about R squared or anything like that? All right, let's go to the next one. Okay, so now we're into this week's stuff. And this week's stuff was on multiple linear regressions. So last week we did the single regression. That one is pretty straightforward. There's a formula. We talked about these squared errors. The multiple regression is exactly the same thing, but now there's more than one. And unfortunately, that makes it much more complicated. So the first question I have for you is, what is the interpretation of the coefficients? So you do a regression, you get beta 1, beta 2, beta 0. And what is the interpretation of these things? Of course, all three of them are estimated, so I really should have written them with a hat, but I got lazy. But I gave you 4 options here on what is the interpretation of beta 1 in the regression. You can read them all and think about what you think it is. What is the interpretation? And also think about what is not the interpretation, because it's easy to get confused. So take a few minutes, read all 4 of these options, and then vote. Okay, maybe I will add one thing. So I said y equals beta 1 x1 plus beta 2 x2 plus beta 0. What I mean is that I did the regression of y on x1 and x2, and this is what I got. So in case that wasn't clear. Okay, so we're up to 7 people. Maybe I'll wait for 1 or 2 more, and then I'll, okay, now we're up to 9. Okay, let's see what people think. All right, 4 or 5, it's a total split. Okay, so 6-4, so pretty split between these two. So the 2 that were wrong, and that you guys correctly identified were wrong, one of them had the word causes in it, and you can never say anything about causing stuff from a regression. So that's, I think this is like the internet is nowadays pretty good at making sure people don't accidentally buy too much into causation, but this is sometimes you'll fall into this trap. It'll feel like one thing is causing another thing, but very often it goes backwards. You can get tricked by this even at a high level. So even with like medical stuff, like this causes some bad outcome, even medically, in your data, you might have a selection effect where only the very bad people end up at the hospital, and so like the causation will end up being like backwards. So you really got to watch out for this, and always kind of keep that in mind, that we're never trying to do causation directly from the linear regression. There's a quote though that I really like that's like, of course the linear regression never says the causation happens, but it does wink suggestively and point and say, look over there. So of course it has something to do with causation, but don't fall into that trap, which none of you did, so that's very good. And what was the first one? What was the other option? Okay, one of them didn't say anything. So it said when x1 increases by 1 unit, the value of y increases by beta 1 units on average. Nobody selected that one, which I think is good because you guys watched the video, you know what's going on. But this one is a common, like, tempting one. And the problem is that when x1 increases by 1 unit, it might also affect x2. So if x1 and x2 are very correlated, it might affect that. And so when you increase x1 by 1, x2 also goes up by 1. And then y has gone up now by not beta 1, but beta 1 plus beta 2. And there could be other variables that are going on, which is why you guys narrowed it down to the last two answers. And definitely one of these two is correct. But which one? Well, it's split 50-50, so we're going to do my favorite thing, where you guys talk to each other and try to convince each other what's going on and let's get some nuance here.
I said just x2,
Okay, let's how about, for example, x1 has got say some dependency with y, or x2. So in this case, even if you keep connecting with them, okay, but if you've got like y and x1 correlated together as change with it. So even if the situation so this is the thing,
Beta 0, beta 1, beta 2 are 1. Beta 0, so x2 is regardless of everything else.
Yeah, you want to read the, yeah. Yeah, I can try to zoom it in a bit too. Oh. Oh, okay, I'm not going to do that.
I said only x2.
So what's your reasoning?
Well, I know one of the two. No, I think, I don't know, my only thought was maybe that when x1 is defined, there is some input from outside variable. So when you change x1, you're technically changing those other variables as well, because they're linked. Even then, so it's just keeping x2 constant because you're assuming those are independent, but you can't assume that all of the variable outside.
So to make things concrete, let's throw in a variable x3. So let's pretend there's three variables. There's y, x1, x2, and x3. And in this question, we're talking about the regression y on x1, x2. So let's do this. Beta 1 x1 plus beta 2 x2 plus beta 0. And like you could imagine in a hypothetical other situation, you actually use x3, right? So let's do that one in a different color. Let's do that one in yellow. Beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 0. And so if this is the specific setup, then the question is actually asking, in our question, is the interpretation of this beta 1 is x1 increasing by 1, x2 is definitely going to be fixed, but are we going to allow x3 to change or not? That's really what it comes down to, right? Are we saying that the beta 1 means the x3 has to be fixed as well, or is the x3 like going to change with the x1 in the way that it likes to do? That's really the question. So hopefully maybe that makes it a little more concrete. Let's go back to the vote. And let me open the vote again. And you can put in what you think. And again, yeah, don't pick the first two because we know those are wrong. And then we'll have a little debate here based on the answers. All right, we're at 7. Maybe I'll wait for like one more answer, and then I'll reveal. Okay. All right, so we're still 5-5 exactly, 6-5. Okay, so let's hear from people who voted for each. Let's tell me why you voted for the one you voted for. So I guess the debate is: do we, when we're going to increase x1 by 1, and we're going to think of keeping x2 fixed, and the question is, do we think of x3 fixed as well, or do we let x3 do whatever it wants to do when you increase x1 by 1, right? So you can imagine that x1 and x3 are like highly correlated. So when you increase x1 by 1, that often leads to a little increase in x3. Should we count that little increase in x3 or not? That's the question. Anyone want to say yeah?
I would argue that you because x3 is not part of the model,
Yeah.
you let it do its own thing. So any change in x1 that also causes a change in x3. That's what happens. When x1 changes, x3 changes as well.
Okay, so
you don't keep that.
So the key part is because x3 is not part of the model. So you're going to allow it to change. Therefore, allow it to change. Okay. So I mean, I understand what you're saying. It seems plausible, but like if someone says like why, like what would you tell them?
Because when you're defining the model that we do have,
Yeah.
x3 is already baked into x1.
I see. Okay. So you're saying like somehow the effect of x3 is going to be baked into here, and so like
Yes.
when you gotta, that's why you gotta allow the x3 to change. Okay.
Yes.
So why is it that we don't allow the x2 to change?
Because we assume that it's independent from x1 because it's also in the model.
Okay. So yeah. So let me add this to the thing. So since x2 is in the model, we assume it's independent of x1. Okay. Anybody else for the other side, or yeah, maybe.
I just wanted to support this
Yeah.
argument,
Mhm.
is that if we're considering x3, then we're adding to the complication
Yeah.
of the analysis here, so it's gonna be, I mean, this is like codependencies within the same model.
Right. Yeah. So this is the thing that we're trying to disentangle, right? So somehow x1 and x3 depend on each other, and we're just trying to figure out what did we actually do when we did this one without leaving x3 out. Did we somehow include the x3s automatically, or did we just like delete them? Like, because it seems like we deleted them, right?
Yeah.
So what exactly are we doing? And that's exactly this question of what is the interpretation of the beta one? I'm not sure if I answered your question.
I think you did.
Okay.
Yeah. But I don't know what we're doing.
Yeah. Well, I think this is why it's exciting when it's split 6-5. That means that half, like everybody's going to learn something, or at least half the class will learn something, and probably the other half isn't too confident either. So everybody's going to learn something. Okay. Anybody else for the keep everything fixed? So 6 people voted for that. So here's I think is a strong argument for the keep everything fixed. What if it was just what if we only had y and x1, right? Like nobody gave us x2 and x3. We were just doing y and x1, and then we did the regression. What would the coefficient mean, right? Well, okay, of course we're changing x1, we got to keep everything else constant, right? Like there is no other stuff, we can't change it. What would it even mean? So it's very I think the keep everything constant one is quite intuitive actually. Anyone else want to add anything to that side? Six people voted for it. Who? Nobody wants to say why?
May I ask, is this
Yeah.
related to the forward,
Oh yeah, the forward
The
selection.
forward, yeah.
So it's definitely related to selection. So I think you should think of the forward selection and the backward selection are methods to try to find a way to choose which ones to pick. And what we're talking about is really, really closely related to how does the choice of variables affect what you get, right? So we're really at the heart of that issue. We're not really talking about forward versus backwards. That's really like a method to pick once you understand what we're like doing about. But it really is the heart of the issue. It's like, what is including or not including x3? What does that actually mean? What are we actually doing, right? Yeah. So does anybody else want to say anything about the other option? Yeah.
I have just one question.
Yeah.
Maybe it's late to the answer, but you know, when we keep, let's say, x to a constant.
Yeah.
So, but we increase x1 by 1.
Yeah.
So, in case there's going to be a change independently by x3,
Yeah.
so the amount of y would be changed more than beta 1.
Yes. Okay. This is a fantastic argument in the favor of this everything, right? Let's just look at the actual equation, right? These are supposed to be equals, right? So I guess you shouldn't. If you put an equal sign, you better put like an epsilon at the end to account for error, right? So of course y is not actually equal to these things. It's equal to that plus some noise. But we tried our best to make the noise as small as possible. And just look at the equation, right? If you increase x1 by 1, then y goes up by beta 1. That's how numbers work. Over here, right, if you also did an increase in x3, then it wouldn't increase by beta 1. It would be beta 1 plus beta 3, right? Supposing they were like very correlated. So it really does seem like you better keep x3 constant as well. Otherwise, look, you're going to increase by more than beta 1. So like, if you want the increase at the end to say beta 1 unit on average, then you really should keep x3 constant. This also seems very plausible. So let's put this one in quotes over here. If you let x3 change as well, so if you let x3 change as well, then the increase would be beta 1 plus beta 3. It wouldn't actually be plus beta 3, that's like supposing they're sort of perfectly correlated, but maybe it would be beta 1 plus a half beta 3 or something. Plus, let's say beta 1 plus, I'll say like the correlation of x1, x3, beta 3 or something like that. So the final little sentence here wouldn't say beta 1 unit on average. Okay. These are both fantastic. I think you guys are thinking about it very critically. This is great. And again, this is the reason this is so important is because when you do a regression, like understanding what variables to choose is really important. And in fact, on Thursday, the whole day, there's like we're going to fast forward to chapter 6 and talk only about this like forward and backward selection and how you should do the selection. So that's what we're doing today. We're trying to understand how does choosing the variables affect things. And both of these have some truth to them, but one of them has a serious like hidden secret mistake somewhere. Okay? And I'm not going to tell you which. So think for a little bit, talk to the people, but one of these two has a secret mistake that is like, it's very tricky to find, but once you find it, you go, aha, okay, it's all clear, and you'll see exactly what's going on. So take 2 minutes here. We're going to do one more vote, and we'll see where is the secret mistake. Yeah, you should feel free to chat or ask questions. Okay, maybe let's do it as a class. Who thinks they know what the super secret mistake on the board is right now? There's something that's very misleading that I wrote on the board. did it very subtly, and I tried to hide it as best I could. Yeah, there's something really misleading. Yeah.
Is that x3 technically is part of the model if you have the error terms in it?
Okay, yeah. Okay, this is a good point. So somehow when you don't include x3, the effect of the x3s is for sure getting baked into this epsilon. So it's not that the x3s are totally gone from this line; they're somehow in here. Right. That is true. That's not what I'm thinking. There's a more serious misunderstanding about what is written on the board, I think. And it has to do with bad writing of math that happens all the time. In real life, you got to be super careful. Anyone else want to take a guess? So I wrote beta 1 x1 in here. I wrote beta 1 x1 here. Are these the same beta 1 x1?
No.
Someone is saying no. So why not?
Is it because of the hat?
Okay. So you could think maybe the thing I forgot is the hat. So it's true there should be hats everywhere, but that's not the mistake. So pretend there's hats everywhere if you want. So the hat means it depends on the data, but I'm going to use the same data for both. But fundamentally, this beta 1 is completely different than this beta 1. They look very similar. Yeah.
Well, it's beta 1 given that x3 isn't in the model, or beta 3 isn't in the model.
This is exactly the thing. So these beta 1, beta 2, and beta 0, when you write them out, you kind of pretend in your head, oh, they're like something in the nature that I found, right? Like beta 1, x1, the coefficient in front of beta 1, I just stare really close at the board and I look only at beta 1, x1. And I say we're looking for the value of beta 1. It exists in the wild, we find it. But beta 1 on its own doesn't make any sense, right? Beta 1 is only part of the entire thing. So beta 1 is actually, this beta 1 in white is actually beta 1 of this whole thing, right? It's beta 1, it's a function of doing regression with x and y. Right? So it really depends on the fact that we chose to do x1 and x2. This beta 1 depends on x1, x2, and x3 regression. So actually, even though they're both called beta 1 and they both appear in front of x1, they really are completely different animals that you should think of. Of course, they tell you the same kind of thing, but they have very different interpretations. And so this is the problem with this argument over here. When we said the answer shouldn't be beta 1, it should be beta 1 plus however much x1 and x3 depend on beta 3. That was the yellow beta 1, beta 3, right? And it turns out that the value of beta 1 actually is, if you did it twice, the value of the white beta 1, when you do only x1 and x2, will be equal to the value of the yellow beta 1 plus however much x3 and x1 are correlated beta 3 in yellow. So this is a common mistake, is to kind of think of the coefficients as actual things rather than something that only exists in the specific context. So this argument is wrong. So the correct answer is this one. You want to leave x2 fixed, but you got to let everything else change along with x1. And all of the changes that we see observed with x1, all of those things are baked into this beta 1. Everything except x2 is baked into that, and that's because beta 1 is doing this x1, x2 regression. So when we calculated the value of the white beta 1, we said we're fixing the x2 and we're letting the x1 change. How much does it change things? If you did the yellow one, it would be x2 and x3 fixed. And the resolution is that you really, the beta 1 isn't actually some God-given special quantity that we're calculating. It really is only about this context. And that's really important to know when you calculate it. Okay, related question. So I'm kind of telling you guys that the beta 1s can change values depending on what you do. They can change values, they can change whether or not they're significant. They can completely flip depending on what you do. So maybe it's really important in this equation it's not so important. You really have to take the context into account, and that's why this whole topic of choosing the variables is so important. It's basically your first project is going to be, you have a lot of variables, work on trying to choose the best ones. Yeah.
Sorry.
Yeah.
If we correlate x1 to y,
Yeah.
so it's going to be a line.
If you got rid of the x2.
Yeah.
Yeah.
So, but in case we missed, So
Yeah.
in real world, it is going to be a surface rather than a line.
Right. Yeah.
So in case we keep, let's say, everything constant, we are only changing x1 in
Yeah.
the model.
Yeah.
But actually, if we change the x2 in the surface, the value of y would be changed. It
Right.
is the reasoning I had. So
Yeah.
if we miss one variable in the model,
Yeah.
so I think and the variable changes.
Yeah.
So the value of y would be changed again.
Yeah. So I think everything you said is right. So I think the thing you got to keep in mind is that the betas are also changing. So that when you do this effect, if you do y equals beta 1 x1 plus beta 0 in blue, the blue betas will somehow take into account how the x1, x2s, and x3s all change, right? So this blue beta will take into account like that a change in x1 is associated with a change in x2, and it'll automatically put that in there. And then when you switch to this one, the beta values completely change. So like maybe this beta 1 is equal to beta 1 plus beta 2 or something. But now the interpretation of this beta 1 is that we've taken as much of the effect of the x2 off as we can, right? And so I think this is like everything you said is right. It's just that you can't compare it's very difficult to compare the blue model to the white model. And it's very tempting because they have the same letters and they have it in the same places, but you should be very careful when you do that, right? They really mean different things. Yeah, so they can change. This is the point. Okay. Yeah, no, it's a great question, and this is like exactly what I want you to be thinking about for this class. Okay. Any other questions? So the next question is super related to this, and it's just a true or a false. Where's the true or false? I have a true or a false. True or false, and it's exactly, they're missing a plus sign. Okay, so I'm missing a plus sign here. There should be beta 1 x1 plus beta 2 x2. It really is supposed to be the equation in white. True or false, if the beta 1 is positive, then it has to be positive in the next one. So if the blue beta 1 is positive, then is it true that the white beta 1 is positive? So far I've said they can change. Can they actually change from being positive to negative? Can it be like a positive association over here and a negative association over here? Okay, and it's just a true-false question. So you have two options, and I'll open that up. So far we've said they can change, and you got to be careful when you're interpreting them as keeping exactly what is in the model fixed and nothing else. But what about the sign, right? The association of the things. Okay, so I'm up to 6. Maybe I'll wait 2 more minutes. It's a tricky one, so think carefully. All right, I'm up to 8. Okay, let's see what people think. All right, 9 people on false. False is the correct answer. Okay, again, it's not showing, but it is false. So beta 1, not only can it change a little bit, it can completely flip sign. So it can be positive in one and negative in the other. And you really got to think carefully that when you calculate regression, you are thinking of it only in terms of the specific variables you chose. And so for the rest of the class, I have an example of a notebook where it does this kind of thing. And so I want to show you guys that. And this is going to be kind of a little bit of a warm-up for your project as well. So it's kind of like I have a data set. I'm trying to fit the best variables I can to it and find the best answer. It's very similar to the project you guys are doing, but I only have like 3 variables. You guys are going to have like 30 variables. That's what's going to make it harder when you do it. So let me find my Python. Okay. Okay, let's open this in Colab so I can, unless I already do. So this one is called multiple regression scrap work, and it's kind of like a rough, I'm just getting the answers, and then maybe next class I will turn it into something nice that'll be more like what you would submit. But for now, let's run everything. Okay, and I'm gonna start by doing it here. So So again, I have a little function called secret data that makes the data, but you guys are going to download the data from Kaggle, and it's going to have a bunch of stuff about houses. So each dot will be a house, and we're measuring y is the price of the house. Of course, that's what we care about when we buy or sell the house. And x1 and x2 are features about the house. And this is a plot of x1 versus y, which I didn't label the axes because I was lazy, which is not good. But so this is x1 and this is y, right? Very nice plot. And the thing, this plot, it's not like a nice Gaussian blob. So a lot of these kind of models work very nicely if it's Gaussian. It's something else. And so the thing you can ask yourself, and the thing I'm going to ask you, is do you think that increasing x1 increases y or does it decrease y? Like if you're going to buy a house and you have the option to make more y's, I don't know, what is y? The number of bedrooms or something. Do you want more or do you want less? I guess number of bedrooms is probably obviously going to increase the price, but think of something where it's tricky. So based on this graph, do you think increasing x1 increases or decreases the value? And I have a little thing here. You could change x1 by 1 unit. Do you think a change in x1 leads to a positive change in y or a negative change in y? And you can this question you can kind of think of as asking, is the coefficient in front of x1, is it positive or negative, right? I'm asking you, is the coefficient a positive coefficient or a negative coefficient? Okay, and this one, I will say, it's not a precise question, right? I didn't say, do these exact things, is the answer positive or negative? This is like a feel question, right? Do you think it should, morally speaking, increase it? You want to see the data again, probably? Yeah, let me show you the data again. Where's the data? Okay. There's the data. Yeah. Okay, I'm up to 9 responses. Let's see what you guys think. Okay, 3 people think it's a positive, 7 people think it's a negative. And the real answer is it could be either. And the real, what is going on here, I'm basically asking you, is the beta positive or negative, right? But I didn't say which one, right? So the blue beta might be positive and the white one might be negative. So to answer a question like, does a change in x1 lead to a higher y or not? It depends in what context. What else are you leaving fixed? And so there's 2 ways to answer the question. One is, let's only look at x1. So if you do y equals beta 1 x1 plus beta 0, like I have in blue on the board, that's saying we're only looking at this graph. In that case, I think the answer is positive, right? You do a line like this, the slope is going to be positive, and that's because if you're a higher x1, you're more likely to be in this group up here, it should be positive. But a lot of you, I think, said negative because you're like, well, look at each group, right? It has a negative slope. So somehow if you leave which group you are in constant, and you say, like, I'm not going to flip-flop between groups, then the answer should be negative. Whereas if you are allowed to flip-flop between groups, then the answer should be positive. So what's the moral of the story? It's not that there's a right answer, that negative or positive is right or wrong. It's that the answer is it depends on what you leave fixed, right? And what other variables you include in your regression. And that's why this stuff is so tricky, right? Otherwise, if it was always just one answer, then the computer could just do it and we wouldn't need anybody to think about it. Okay, so the answer is it positive or negative? The answer is it depends. And to really investigate, you gotta start actually doing these regressions and seeing what comes out. So that's what I'm gonna do here. And so what I did is I made a data frame out of this. So a data frame is just a bunch of vectors that are stuck together with names. So they have the names x1, x2, x, and y. This was all in the notebook that I posted last time. So if you've never seen stuff like this, you should check those out. But I think you guys are pretty good at programming, probably even better than me. One function that I discovered from that notebook is this pair plot function from Seaborn. And this is a nice thing because it lets you see all the variables together. So I have x1, x2, and y, and this is a little 3x3 plot with all the possible pairs. And on the diagonal, it shows you a histogram. So you can see this is the x1 value is pretty flat. The the y value has a nice peak around 0. But the x2 value is this kind of thing that's like either on or off, right? So, and you can actually see like what the plots are doing, like the x2s kind of, you can vertically split the groups by their x2 value. So this is always a good idea sort of before you start, is to look at the data so you can try to tell these things, right? So don't just go in blind. But here is the regression for y and x1, right? This is the thing that's on the board. Okay. Okay, go back. Okay, and it gives you a bunch of information. So first of all, I'm using a little thing here, which I think those of you who like R will like. So this lets you type in a formula, like an R formula, and it does the regression. There's other ways you can specify it. So for example, if you want to try all the possible things, there's like, you can make like a loop to go through, like just try a bunch of stuff, which might be useful. And it gives you kind of way too much information about the regression, right? Like, I just want like a couple things, but it tells me a whole bunch of stuff, like the date, the time, the stuff like this. So sometimes you gotta close your eyes and ignore the right things. What are the things that I think are important? Let me try to get it all on one page. There we go. So the R squared is good for comparing this one to other regressions of the same thing. So the R squared sort of on its own isn't very helpful, but when you're comparing, it's helpful. If you want to know significance, there's a lot of different ways you can do it. Like, for example, the F statistic can tell you if it's significant. But my favorite way, like I said, is to only look at these things, which are the confidence intervals. So the intercept, that's the beta 0. The confidence interval is between minus 2.75 and minus 0.7. So that's significant. That's telling me the intercept. And the effect on x1, that's the coefficient. That is between 0.25 and 0.6. So because it's kind of not including 0, that's a significant effect. In the sense, statistically significant. It's not likely to be due to chance. And the main estimate we have is 0.43. That's 0.43. And another way you can see what's going on is to like plot it. So this is a good way to do it. So I plot the orange line versus the blue line, and you can see it's positive. So those of you who said positive, if this is what you were thinking, you are correct. And you can see it's actually kind of not doing a great job of capturing what's going on, which is why the R squared value is pretty low, right? It's 0.2. So now the question is, can we do better? Can we include some other variables? Yeah?
All right, so R squared, 0.2.
Yeah.
I think, to me, it means that, okay, the model only interprets 20% of what is going to be happening.
Yes.
So is it enough, I guess?
So okay, so this is the problem with the R squared. So I agree, the model is telling you something like, it's only telling you 20% of what happened.
Mm.
But the thing you don't know is it telling me 20% of what happened because I could have been doing 90% and I suck and I'm doing 20% instead? Or is it telling me 20% because fundamentally this is like a really noisy thing and like nobody could do higher than 20%? So that's the like real problem with R squared on its own. R squared as a comparison is great, right? Because if you have a model and I have a model, let's go like head to head. Who's got the better R squared? Let's see. But if it's like, you just want to know like, is it good or bad? It's not going to tell you that on its own. And again, the real reason is it because it's impossible to like predict the data, it's just random noise? Or is it that my model needs more help?
Yeah, and another question, the previous figure
Yeah.
has to do with the, let's say, intercept and also coefficient.
Yeah.
Am I right?
Uh-huh.
No, the figure.
Oh, this one.
No, some.
All the way up.
Yeah, this one.
Yeah, so this is just plotting the data.
Okay.
These are just,
Okay.
so it's a pair, every pair. So the one I showed you before was x1 versus y is this one. And these are all the other ones. So there's x1 and x2 in this problem. Yeah. Okay. But yeah, this is great. This is a great comment about the R squared. Like, you really should only ever look at the R squared when you're comparing it to another model of the same data. Which is another way of saying you should only ever compare the value of the residual sum of squares to each other. Okay. All right, so yeah, this was one thing. Okay, yellow line. Let's try y versus x2. So if you do y versus x2, that's this plot. It's kind of similar, right? So you're like, well, can we do better with y versus x2? And you try and you get 0.6 as an R-squared. So kind of y versus x2 is a bit better than y versus x1. And everything is significant, right, between 4 and 5.5. So this is like the parts that I like to highlight. I basically ignore everything else. I just highlight the confidence interval. Again, some people really like the p-values if the p-value is less than 5, but I just like to look at the confidence interval. That's more intuitive to me. So okay, that looks good. But same kind of plot, right? We kind of got these two groups, and we do them. Okay, and the thing I want to point out is that the coefficients were always positive, right? So for x2, it was 4.7, and it was significant. And for x1, the coefficient was 0.43, and it was significant. So positive associations, right? Bigger x1 means bigger y, bigger x2 means bigger y. But the thing you got to watch out for is that when you do both, now everything is different. So here is y against x1 and x2. That's the white thing on the board. And now, again, everything is still significant, so confidence intervals never include 0. But now the coefficient in front of x1 is negative, right? And so, again, what you really should think is that the coefficient depends strongly on exactly what variables you chose. And what this means is that in the context of keeping x2 fixed, the association of x1 and y is negative now. So how can we see that? And again, our R-squared went up, so this is a better model from what we can tell. So how can we see that? So here's what I did. So before I was plotting y versus x1 and y versus x2, and the orange line was what we predicted. So let's try doing that again. So let's do y versus x1 and y versus x2, and we'll plot our prediction. And if you do that, that's what this code does. You get this kind of funny thing. So the data is the orange line, and my predictions are this like blue chunky thing. Does anyone know why you don't just get one line? Yeah. Yeah, really, what we're looking at is a plane, and we're looking at it from one side, right? So if you look at a plane from one side, there's sort of the top of it, and then there's the bottom of it, and you would have any value in between. And so you can see the plane is sort of capturing both things. And so to better understand it, this is not a great way. You can't really look at x1 or x2 on their own, which kind of makes sense, right? If you're doing x1 and x2 in the regression, you need a way to combine. But so another good way to look at it is to plot the residuals. So instead of plotting what this is, I'm going to plot the prediction for each point. Our model has a prediction for each point. You could do a 3D plot. That's another way to do it. But that will also fail you when you go to 4 dimensions. So plotting the residuals for x1 and y, that looks like that. Those are the residuals. And you can see the residuals will always have average 0, right? If I add up all of them, they're going to have average 0. But maybe there's some kind of pattern in where they are. Right now, there's no pattern. So it looks good. And you can plot this kind of thing. And using this plot, what I did is I drew a little line with a triangle at the prediction. So you can see it's kind of working. And what it's really doing is there's kind of a line over here that it's predicting, and a line over here it's predicting. So once you factor in the x2 in the regression, the x1 slope is negative. It's exactly the slope of these groups. And sort of the x2 tells you which line you should use, this line or that line. So this is exactly like what we were doing. The beta 1 flipped from being just positive on its own, if you do beta 1 with just x. Now the beta 1 is negative, because once you're controlling for the x2, you know which group you're in. Okay. And you can see the same kind of thing with the x2s. So this was all for x1, and that's like the story of the flipping beta. Let's look at the x2s. So these are the residuals. And this is what the thing looks like. And you can see it's a positive slope. There's something like this going on in these groups. So first of all, any questions or comments about that? So I think that the main thing I want you guys to take away is that it really depends on who you do the regression with. Who's in the regression is really going to affect the values you get and whether or not they're significant and stuff like that. Yeah?
Sorry, so if you have got, let's say, m parameters, m estimated, so we need to, let's say, plot residuals, m residuals, y per x1 to xm.
I think this is like a good place to start, right? Yeah. So of course things sort of don't get linearly more complicated, they get sort of exponentially more complicated. But it's for sure it's like kind of low-hanging fruit to plot these residuals and see what you can see. And in fact, this is the next point I want to make. Do you guys see a pattern in these residuals, in the x2 residuals? So the x1s, that looks pretty good. It's like a blob kind of equally likely to be plus or minus, like we're essentially plotting what the model thinks the epsilon is, right? And we would like the epsilon to just be like pure random noise. Like we would like to say we've got the model as good as we can, the only thing that's left over is this like random junk noise. If there's a pattern in the epsilon, then maybe we can find the pattern, pull out the pattern, and have a better model. So I think there's no pattern in this one, the x1s. Do you guys see a pattern in the x2 residuals? Is there a pattern there that we can exploit to get a better model? That's what we want to see. Do they look like they're just randomly all over the place, or is there like kind of some kind of structure going on? Yeah, what do you think?
Yeah, different structure. Like, yeah.
What structure do you see?
2 categories.
Well, so there's 2 categories. This is true. But this is, I mean, the fact that the x values are just whatever the x2 values are. So there were 2 categories sort of to begin with. But do you see a pattern in the y values? That's like, that we can use, right? Because there's sort of like, what we're plotting here is the epsilon. If the epsilon is pure noise, we can't do anything. But if we can find the pattern and kind of like get rid of it here, we can help. You're definitely on the right track with this categorical idea. Yeah.
The slope is somehow high and negative.
Yeah. So kind of the pattern is the ones on the left side of the group are all positive. We've sort of overestimated all these ones, so we have positive residual, and we've underestimated all these ones. Wait, what round was the other way around? This is the difference between the true value and our guess. So that we've underestimated these ones and we've overestimated these ones. And so if you see a pattern like this, you're like systematically overestimating some part of your space, and you're systematically underestimating another part. And this means that you can probably fix something by like letting it know where you are in here, right? Another way to see that is to go to the plot over here. So we sort of have, this is somewhat narrow. Like, of course, there's a range in the x2 versus y because the x1 can be anything. But we're essentially going like a line like this, right? And when you do a line like this, let's draw it on the board. Okay, let's do it in white. So we have our 2 groups of data, sort of here and here. And the line is in blue. So again, we don't have a line, we actually have a plane, but the plane is somewhat narrow, so you can kind of think of it as a line. And if you're connecting the dots like this, you can see that you're sort of systematically, these ones are above, whereas like these ones are below, right? Below. And you have the same kind of thing over here, above and below. Okay, and of course it's not perfect, right? But it's like a pattern. Do you guys see this pattern? So when you try to kind of fit this thing with a line, you're kind of systematically messing up. And again, I think it's really clear in these residuals. If you look, we're overestimating on the left side and underestimating here, and then vice versa. Okay, so how would we fix it? You see this, you realize, okay, this model is screwing up. How do we fix it? Yeah.
We made a dummy variable.
Okay.
Let's say to the model x3.
Okay, so we're going to make an x3, and what does x3 do? Let's make an x3. x3. What should x3 do?
I think it's going to be a categorical dummy variable, by 0 or 1. And then we run the model again and see how it works.
Okay, but there is no x3 with 0 or 1, so you want to create it? Is this what you're saying? Like, how do I decide if it's 0 or 1?
I made a mistake. I used the residual amount for that, so.
You want to use the residual?
I don't know.
No, you're on the right track. I'm giving you a hard time, but you're actually, this is a great idea. Anyone else want to take a stab at it? So this is a good idea. Let's make an x3. And how is that going to help the model? Like fundamentally, what is the x3 going to do? Right?
I just wanted to suggest to remove some part of the residual as a variable to the model. It is why I suggest like this. But
yeah. Okay. So I think what you're thinking is like these ones that are above, put those as 1, and these ones as 0 or something, right? So if you do that, what you're letting the model do is like fill in a line above and below, sort of like that. So that's one thing you could do, and then it could try to fix the thing. So the way you're suggesting it is definitely on the right track. I think you got to be careful with overfitting, right? Like, of course, it's possible by fitting a bunch of variables like this. Every time the residual is positive, let's subtract a little bit from it. Every time the residual is negative, let's add a little bit from it. Eventually, you're going to fit the data perfectly, but you're going to have like a really overfit model. So this kind of thing is a good idea, but I think there's another way to do it, which is that, what if, right now, we're fitting one line for these two groups? What if we fit two different lines for the two groups, right? What if we just say, so again, you shouldn't erase the data, put the data back, but instead of doing one line, why don't I do two lines? I'll do one line for this guy and one line for this guy, like that. And then that way, maybe the slope isn't so much. Right? And then that way I'm allowed to have a jump between the two groups. The x3 will tell me which group I'm in. And I can clearly see in the data that there are two groups, so it kind of makes sense to add this as a variable. And you can add it in and see what happens. So this is a good thing. So 0 if on the left, let's say left group, and 1 on the right group. Okay, and again, you have to be careful with this kind of stuff because maybe you're overfitting by doing this, but it's worth trying when you see this in your model. So I see this pattern in the residuals, so I'm thinking, let's add a feature, right? And I made the feature x3, which is just whether or not x2 is bigger than a half. This went to sleep. Great. Whether or not x2 is bigger than a half. So all these ones on this side, these ones all get a 1. These ones all get a 0. And will it allow me to do stuff? Okay, so now I have the fit. I have x1, x2, and x3. So by allowing an x3, a categorical variable, you saw this in the video, basically you're allowing jumps in your line. And this is like a way to think about it. So I'm allowing the model, it has the coefficient beta 3 will be 0 times beta 3 over here and 1 times beta 3 over here. So I'm exactly allowing a line with a jump of size beta 3. And I let the computer, by doing the regression, can choose whatever value of beta 3 it wants to kind of best fit the data. Okay, what happened when I did that? Okay, so this is what we got. First thing to notice, the r² went up to 0.9. That's promising. Second thing to notice, so here it's telling me t.true. It's doing this categorical thing, so that's working as intended. Let's look at what's going on now. So x3, very significant, between 9 and 13. So it's telling us this is like a solid jump here. It's not just like, oh, it's mostly aligned, like a tiny jump, big jump. The slope of x1, still negative, still significant. But now what happened to x2? x2 went from being positive to now it's slightly negative, but actually it's not significant at all anymore. And so what it's kind of saying is that the slope is actually flat now. The slope is like flat now. Right? In the x2 graph, it's a flat line. There really is no trend, sort of. It's flat. The only thing that is this jump. So once you include the jump, you sort of don't need the x2 anymore. The x2 is no longer significant given that x3 is in the model. And we can check again. You can plot the residuals, and now the residuals are nice and no pattern. We got rid of the pattern in the residuals. So this is great. We have a better model. The very last step I would do, and then this will be the last thing I do because we're out of time. Does anyone know what I would do now if I was a real data? This is like your project, you're working on it, you're selecting variables. We did x1, x2, and x3. We added x3, it's working very well. What would you do now? Yeah, you got to do all the work, but there's one more modeling thing we can do that's like better. I'll give you a hint, right? When you see something like this, when you see these 3 lines, there's something that should jump in your brain immediately. So x2 is minus 0.56, but the confidence interval is from minus 2.7 to 1.6. Yeah, it's including 0. So x2 is not significant. x2 is just like, basically there's like noise in our model and we're fitting to the noise. We're kind of overfitting with the x2. The x2 doesn't actually help anything. Once you know x3, the additional information of what is the exact value of x2 is actually maybe not helping. So the last thing I would do is I would try doing it without x2. So I added in, you know, obviously start with x2, that was the variable, but now that I have the x3, and that's working better, let's try it without the x2. And I think that's the last thing I did. Maybe I didn't even do that. Okay, that's what I would do. And okay, here's the thing. When you delete things, of course the r squared is going to go down, right? Is that better or worse? If the r squared goes down, that's the topic of Thursday's videos. So we'll go watch all the videos on Thursdays, and we're going to talk about how you actually check if you're making progress or not. But you are basically set up now. You guys should practice running this kind of stuff for the Kaggle housing data set. That's due a week from Friday is the draft. Okay, see you guys on Thursday.